Okay, so let's pass over this code. Then you get the generator and you get the public key. You want to find X. So you run over, I is running from 0 to the square of Q. Okay. Every time H is multiplied with another step. You see, here is the step, this M. I is going one after one, but you are looking at G minus MI. So you put this on a table, on a hashing table. Then this is the giant step. Then you go over with baby step, and you always compare between your iterator, which the iterator is G in the power of J. It begins with G0 and goes to until M. Now, as you see if it's true, if this return the value of 1, then you return this X. Now, in the example here, I took Q to be this odd number. Okay, so how many elements you have in the order group? 100, because you always remove the 0, and of course 101 is a 0. So you have 100 numbers. Your steps will be of 10. Then this line, it's the line of the giant steps. Now, I don't keep it like this. I actually do some hashing table. Maybe like this. When I put I, not I, the least significant digit. Okay, so it can, since we go until 10, so we have M slots, because I have M steps, so I want the complexity to be in average 0.1. So if I have 10 jumps, so I take 10 slots.
By the way, the worst time complexity, is it still N? I'm not sure.
Yes, it's N.
Okay. Right. Yeah, it makes sense.
Now, I go, the first step is this one. So I put it here. Now, of course, I remember the I that bring me to here because I need it. Okay. So here I keep it 0 and 37. And then I see 13. I put it here. It's 1 and 13. And then I have 81. It's here. And here, this is called collusion. So this is some bad, but it's not so bad because it's happened rarely. Okay, I put it in a link chain. Okay, so when I will get here 3, I will have to pass through the 2 of this. Okay. But in complexity of O1, each one here is, I compare to 1. This one, okay? This one, I compare it to 81. It's not the same. 1, it's not 81. Okay? Then I go to 3. 3 are these 2, 1. 3, it's not 13, it's not 23. Okay? 9, it's not, I mean, if I went further, there is no 9 here. 27, there is no 7 here. 81, it's again 1. So here I have a comparison, true. Okay, so in 81, I see it's the I is 2. Okay, so here I get comparison true. So I know that H, okay, is the generator 3 of minus 10 times 2. This is the I. Plus, no, it's plus here. It's not minus because we have already divided. Plus our baby step, which is 4. J is 4. So this is the answer. I mean, 3 in the power of 24 is equal to 37. Okay. Okay. Now, how can we avoid this attack? Okay. Okay.
Can you repeat quickly about the hashing table? How did you get those values?
Yes. I mean, every time I got a giant step, I put it by the least significant digit. This I put it in the 7. This in the 3. This in the 81. So once I see here 81, I don't go over all possibilities. I just go with to compare with those who finish with ends with 1, and also here and here and here. So in the average case, every time I step here, it's only 1 comparison. Because in the average case, okay, the length of the collision list is, I mean, it's of complexity 1, not more than that. Okay.
Okay, thank you.
Just a minute. Okay. Now we are going to see a very popular algorithm, which is called RSA. RSA is after 3 Jews, Rivest, Shamir. Shamir is an Israeli from Machon Weizmann, and Edelman. I think, call it like this. This was the most popular algorithm until, a few years ago. I will explain you what was the attack that made it less popular, and we're gonna see how we can avoid this attack. Okay. So what is the RSA? It's basically based on the order term. Okay, so let me remind you what order says. Order says, of course, he didn't speak in this language. I mean, this is a modern language, but he formulates the same thing in another way. Okay, he said that if A is prime to n, then this A belongs to the Euler group UN. And since it belongs to UN, this A in the power of the group cardinality, which is phi n, must be the identity, because any order divides the group cardinality. Okay. This is order. Now, what is RSA? Okay, Alice. Now, this protocol is mainly used not for, as we've seen, clients which are equal, but some server like the bank and many clients. Okay, so Alice will be the bank. Okay, so Alice chooses two big prime numbers, P and Q. And of course, these are discrete. I mean, this is a secret. Okay.
Private, so that way. Okay.
Okay. And computes, this is very simple, computes phi of PQ. Okay. N is PQ, so it computes N. What do you think is phi of N? If these are two primes, you remember?
Phi of P times phi of Q.
Which is what? These
P
are
minus P minus 1 times Q minus 1.
yes. Okay. Now this is private. No one knows that. Okay. Now Alice chooses a number D, Oh, number, okay. Okay, such that D will be prime, coprime to phi of n. So if D is prime to phi of n, then D belongs to the Euler group U phi n, not UN, U phi n. Okay, so, and computes E, which is the inverse of D, modulo phi n, not modulo n, modulo phi n. Now, this is known to everyone. This is private. You must understand, I mean, this is private. Okay, this is public. Okay, this is public and this is private. You know, there were so many attempts. Once you know n, to decompose it to the two primes. It's a hard thing, okay? But we're gonna see one way and how to avoid this attack. But if one knows how to decompose n to p and q, you don't have RSA anymore, okay? It's all based on that this decomposition is hard. I mean, public is n public, not pq. The number n is known. Okay. Okay. So now Alice wants to communicate with Bob. So Alice sends Bob the public key. Everything you transmit on the net is assumed to be public. Okay, so this is like an invitation to talk with her. Why do we call it E? Because this is going to be the encryption key. It's like Alice tells B, if you want to do some action in your account or something, you can send to me any message you want. But before you send it, encrypt it by E. Now, this is an asymmetric method. I mean, all knows how to encrypt. No one knows, even Bob doesn't, how to decrypt. So it's in one-way function. I mean, we're gonna see how is it done. But E is gonna be a public key by which you lock your information and you are not able to open it because D remains private. Okay, the decryption key will be D. This D. Okay, this will be the encryption. And this will be the decryption. So everything that I color in green is known, and in pink is not known. Okay, so Alice sends this information to Bob. Now, what does Bob do? Bob sends his message M such that M is core prime to N. I mean, it's not a problem once you have M to put some extra bit, which in a zone that everyone knows that you don't look at it, just to make the all message be, I mean all the messages here are numbers in UN. Okay, so you have a number in UN, so you put some extra bits such that it becomes, I mean, the original M could be any number, but you want it to be in UN, so you put some extra bits and it becomes core prime to 1. You put it in a zone that no one looks at it anyway. So now Bob wants to send M. Okay, so he must encrypt it. So what does he do? Okay. So I would write it wants to send. He encrypts M by just taking the power of E. Of course, everything is modulo N. Now, this is gibberish. Okay, so Bob sends Alice using the data that she gave him. He sends ME, which is E. Okay, now you can say, you can tell me everyone can pretends himself to be B because anyone see that. Okay, this is another problem of authentication. This is solved with another way. But once we know that that this is really Bob, he sends ME, M in the power of E. Okay, what Alice does, and only she can do that. No one else can do that. What Alice does. Alice decrypts E by, she takes this E in the power of D. You remember the D that she has chosen? This is unknown. Okay, D is the inverse of E, but not in UN, in U phi n. But phi n is not known, because if phi n was known, so by Euclides, once you know E, you know D. But this is not known. Okay. So she does E in the power of D. So what does she get? MED. But D is the inverse of E modulo phi n. So it's equal to 1 plus phi n with multiply some with some Q. Okay? Now this is equal to M phi of n in the power of Q. Now what is this? Equal to modulo n. Okay, this is the point. This is equal or equivalent to what? Modulo n. Remember that m is prime to n. So m in the power of phi n is what?
1.
1. So actually you get m modulo n. Okay, and the only one that can use this D is Alice. Now, if one knows this phi n, so once all knows E, they can easily find its inverse by the Euclides. So it's very important that no one knows phi n. Though no n is known, but phi n is not known because P and Q are not known. Okay, this is very interesting. I mean, I give you a box, you enter it, what do you want? I give you the key to lock it, but be careful, once you lock it, you cannot open it. Even Bob is not able to understand what E has been encrypted. What, sorry?
I have a question. So phi n is not known just because it takes time to compute it, because we
Yes.
do know what is phi n if we have enough time.
It takes too much time until one finds it. This was already changed. I mean, of course, if you have many very strong computers, then you can. I mean, if you are something like a state, okay, then you can break it. Okay, you must have a very large. I mean, a very powerful computation power. Okay. Think of primes that are 2 in the power of 200. These very large primes. Okay, so.
But I have a question about
Yes.
how do you construct those, because you showed us that there is the Fermat theorem to how to find the prime number, but you don't look all of the prime numbers. You look at, if you have the formula that generates those numbers, then you have much less prime numbers to look for.
Still, these are many primes possible, many primes. Okay, only to describe these primes, think of you need something like I don't know, 10 lines of numbers just to write the number. Okay, so think how many possibilities you have. Okay, these are very large primes. Okay.
Yes, okay.
And of course, you don't have only Fermat, okay? So I will give you some attack in a second, but first let us summarize some remarks. Okay. This protocol is asymmetric. In the sense that I don't think we need here E, isn't it? I'm not sure. Okay. Knowing E does not give you D. Okay, unlike the Diffie-Hellman. Okay, so this is more suitable for server and clients. Okay, now, secondly, if one decompose or is able compose N to or in an efficient way, then he knows phi of N and is able to compute D in UN using the Euclid algorithm. Okay, this is some disadvantage. Anyone can pretend to be Alice. And Bob. So we need another protocol of authentication. No, it's not like this. I think it's okay. Are there more questions about RSA? Maybe you remember Adi Shamir won some national prize, Pras Israel, a few years ago. He's a very modest person. Okay. Now, Fermat, of course, without knowing this application, tried to decompose numbers to factors. Okay. So what has he done, Fermat? He said the following. Any odd number, okay, n can be described as x plus y, x minus y. Or in other words, x squared minus y squared. Okay, it's not difficult to show that. I mean, you can always, I mean, if n is decomposed to two numbers, then any k and l, so you can find k to be some. It's like solving some system of equation. I mean, if you have here, suppose this is a P and Q. I don't in general L and M. Okay, so it's not difficult to compute x plus y is equal to L and x minus y is equal to M. Okay, so you can find x and y, but you don't know L and M. But you are searching for such x and y, because once you know such x and y, okay, then you know n and m. So if we find x and y such that x squared is congruent to y squared modulo n, which is exactly what happens here. Then x squared minus y squared is 0 modulo n, and then you can write x plus y, x minus y congruent to 0 modulo n. Okay, but it's like saying it's equal to n times some, I don't know, some k. So what Fermat suggested to do, okay, is to take take x, the GCD of x plus y sig n, and okay, GCD. Then you have two factors of n. These are going to be two factors of n. Because these are less than n and divide n. This divides n. Now it's possible that one of these are 1 and the other is n, so we didn't do anything. But in good chance, these are not trivial, okay? In particular, if n is PQ, P and Q are primes, like in our case of RSA, then there is a good chance that this GCD are non-trivial factors. I mean RPQ. you don't have any other factors. Now, how do you find such x and y? How do you find such x and y? I mean, this is also hard. So for this purpose, we have some algorithms. Like, I mean, the most famous one is the Dixon one. So the question is, I mean, I will tell you just another thing. Such a kind of attacks are called general number sieve number field sieve. But these are all based, as we have seen, on this decomposition of x plus y with x minus y. So how can we avoid such an attack?
What is the attack again? To find the PQ?
Yes, the attack is to find x and y such that they're square. I mean, x different than y, than y, of course. Okay, to find two different numbers that their square are the same modulo n. For example, $15 is 3 times 5. Now, we don't know that it is like this, but we see that 3 square is like 12 square, which is 9 modulo 15. So we take 3 GCD with 15 is 3. Okay, and this is our decomposition. Now you tell me, of course, it's easier to find this, but because this is very small, okay? But you can, there are algorithms how to compute, because you don't compute every time from the start. I mean, you have some iterations that you find the power. Okay, I don't want to get into it, but I just want to explain to you why it's important to do some algebraic action, which is the following. I mean, each time that we take, okay, until now, so how can we avoid the general number field S? The answer is extension of prime fields. What do I mean? We knew until now only one kind of finite field. We used UP, which is taking some prime and removing the zero with multiplication. This is what we have done so far. And indeed, this algorithm is a little efficient with this kind of group. But there are other kind of finite fields. I mean, you start by such a field, okay? FP is called a prime field. We may extend it by adding some root of an irreducible polynomial over FQ. And this is what I think I want you to do in your project. By the way, I talked to Tomer. There is no problem that you do it the three of you together. Okay. So what do I mean extending a prime field? Okay. Example. This field, very little field, very small field, contains only 3 numbers. Okay, and U3 is only 2 numbers. Now, if I look at this ring, this is the ring of polynomials in one variable x with coefficients from F3. Okay. For example, I mean, of course, it's infinite ring because you can do you can take your degree of polynomial as large as you want. Okay, for example, I don't know. Okay, this belongs to F3x. But now I take this ring modulo what is being generated by some irreducible polynomial. For example, this polynomial. How do I know that this polynomial is irreducible? I just try. I mean, you only have 3 possibilities. Okay, none of them is a root of this polynomial. So now this is a finite set. It's actually a finite field. What does it contain? I mean, think of all polynomials that can be like this one, but this is 0. Okay, so actually you remain with only polynomials of this way. Say alpha plus x beta now this is the field. Okay, why do I say that all elements here are of this form? Because if you take such an element and you multiply it with another such an element, what do you get? You get alpha 1, alpha 2. Now, instead of writing x squared beta 1, beta 2, okay, what will I write instead of writing x squared? I will write it as -1, because in this quotient, any x1 plus 1 is 0. So x in this power of 2 is -1.
Can you please repeat it? Why is it -1?
Yes. It's actually, you can write it also in this way. Okay, which is actually the root of this polynomial. This is what I took F3 and not F5. Okay, because any 3 modulo 4 does not contain a square of -1, but F5 does. I mean, the same thing with F5, I mean, won't do the job because 2 square plus 1 is 0 in 5. And the same in any prime, which is 1 modulo 4, like 13, okay? But any prime which is 3 modulo 4, this remains irreducible. Okay, so think of this polynomial, okay? In this quotient, I mean, you could write it like this. I mean, x.
I'm sorry, I still didn't understand why is it -1.
Because x square is equal to x squared plus 1 minus 1. So it's congruent to minus 1 modulo.
Okay. Okay.
Okay. So you always remains with only 1 degree of x. Now, if the polynomials were irreducible of larger power, then you always get 1 less. Okay. So now, we have in this the ability to use some programming. This is why I wanted you to have some program ability knowledge. Because how do you keep these field elements in the software? I mean, you can use a class. You know what the class struct? Okay, in this class, you have actually 2 fields. You have the coefficient, the free coefficient, and the one of x. These are all objects of this field. Okay, now you need to use what we call operator overloading. Have you heard about it? Operator overloading. Usually we study it in object oriented. Have you heard about it? Operator overloading. So in operator overloading, you are defining what is multiplication. So you define that given 2 such objects, you get the new coefficient, the free coefficient will be this, and the other field will be this. So you always remember 2 kinds, two numbers in your prime field. The one without the x and the one with the x. Okay. So you actually you're able to implement the structure of the field. I mean, you have here a new kind of multiplication. It's not the usual multiplication. It's the multiplication inside this. Okay.
So it is saved like a complex number, like you have the real part and the imaginary.
Exactly. But it doesn't have to be I. Okay?
Yeah, of course, but the same principle.
Yes, of course. This is how you extend fields. Now, by the way, how many elements do we have here? Think of all possibilities. How many elements we have here?
6.
So how many?
6, no?
No, 6. You have 3 possibilities here. Think of a tuple of a pair of data. You have 3 elements here and 3 possibilities here. So you have
9.
9.
Yeah.
9 possibilities. Okay. Let me show you another example. Take take F5 x modulo this polynomial. Now, this polynomial wouldn't be irreducible if we have taken 3, because 1 and 1 and 1 is 0. But over F5, you have just you can check it that this is, I mean, if you put it 1 or 2 or 3 or 4, I mean, you don't get here 0, you don't get here 5. Okay, So this is again, this again, it's a square dimension extension. Okay, it's a two-dimensional expression. Okay, is like before, but you can think of larger dimensional. So now the multiplication will be a little different. Now, instead of writing x squared, I will write okay. And then you also have so finally, okay, this is no, just delete it. Yes, okay. Hmm. Hmm. Okay, so this is the multiplication. So you have to program it. I mean, to define your operator overloading of new multiplication. This is the new multiplication in this ring, in this field. Okay. Of course, any element here is invertible, because it's not a problem to think. I mean, once you have alpha 1 and beta 1, it's not hard to think of. I mean, you have two equations here to make this 0 and to make this 1. Okay. So any element here is invertible. So it's just the definition of field. I mean, you remove the 0 and you have, with respect to this new multiplication, we have an abelian group. Okay. Now, if you do your, and by the way, this field extension is again cyclic. I don't know if I want to show it. Maybe next time I think if I want to show you why. But any finite field, okay, any finite field, if you remove the 0, you get a cyclic multiplication group, cyclic. So you can use your Diffie-Hellman using this field, but now Fermat doesn't work because it's not modulo n, it's modulo some polynomial, okay? So it doesn't work. I mean, it's not so easy. So this is a much better option. So I didn't think about, I mean, totally, but I want you to program such a thing. I mean, to have some large prime number and find some irreducible polynomial to create this field and do some Diffie-Hellman over this field of this extended field. This is not what is used today. Okay, so this is interesting. Okay, by the way, this field is actually F5 omega 3. Omega 3 is cis 2 pi 3. Why did you? Because if you take this complex number, okay, and the square of it, so the square is actually 4 pi divided by 3, because if you multiply cis with cis, it's like adding the arguments. So you have in the unit circle, whoa, you have here, this is omega square. So the cosinus is half, minus half. So omega plus omega square is -1 because the sinus is being reduced. I mean, this sinus removing this sinus. So finally, it's exactly the solution of this polynomial. Okay. So this is a way to extend field. Okay, to find some irreducible polynomial, and then to describe the elements which are going every time to the degree of the polynomial -1. I mean, this doesn't have to be 2. It can be 3, 4, 5. I mean, you can have many extensions of the field, and this will determine how many elements you have. For example, here, how many elements we have here? We have 5 square. So not only you got a larger field, you also it's not a number field. I mean, it's not a prime field. It's difficult to find the decomposition here because it's not the usual multiplication. I mean, all the algorithms that are known that are very efficient using the usual multiplication. Now this multiplication is another one, okay? So it's much more difficult to attack such a field. Okay, but
you're using this extension to just play with the multiplication?
Yes, but you have to understand that your elements are going to be, in general, polynomials, not numbers. So the generator will be some polynomial, and you take, I mean, you have also to find some generator. Okay?
Why did you need to go through the definition of polynomials? You could have defined a field of not scalars, just vectors, and you get the same extensions in, the extended field, in this extended field.
Yes, but then there are known algorithms to break this, okay? Because the multiplication is very simple. Here, you don't have an efficient algorithm that breaks this because it's not the usual multiplication. Okay.
Mm-hmm.
So why doesn't it use?
The truth is, you know Professor Boris Kuniavsky?
No.
Okay, so he, I mean, I want to show you something. Maybe find it here somewhere. I made some. I mean, there is a way. This is the you see it was you see now the Torus-based cryptography. You see it?
Yeah.
So this is a lecture I gave to Checkpoint almost 10 years ago, and I showed them something more complicated. Okay. I mean, you find some Torus. I mean, maybe I forgot that they forgot mathematics. Okay, they are more engineering. Okay, but anyway, I explained why it is cyclic, and how do you? I mean, I'm okay. This is the attack. You see the attack. Number field sieve is a good attack. I suggested the third line here, okay, which is Torus based. Okay, I want to show you, for example, you see this is a very basic example. I mean, there are two extensions here, one by polynomial x, and after that another extension of polynomial y. Okay, so these are the elements of the field, and this is known as Torus-based cryptography. I asked Professor Kuniavsky why. I mean, in the end of this lecture, one of the heads of the teams there, I mean, there were all R&D there. I mean, all research and development engineering of Checkpoint came to hear this lecture. It was like 200 people. Okay, and one of the head of the teams came to me in the end of the lecture and asked me this question. He asked me, do I know that my suggestion was checked? I mean, by attackers. But I mean, if it's known a good attack that breaks it down. So I told him that this is research. I mean, I don't know. I mean, and he said, we are only developing something that we know that has been checked by the public. Okay, now I didn't understood it at that time, but I understood it later. I mean, every protocol that you do in cryptography has to be checked and rechecked, because you may think that your suggestion is good, but there are attackers that are more clever than you, and this may all break down. Okay, so until now, and neither I nor Professor Kuniavsky, that is more familiar with these subjects than me, and know why this algorithm. It's not me. I didn't invent it. It's a man and wife called Rubin Silverberg that have been developing it. We don't have any idea why this didn't raised up. I mean, it's much stronger and much better than the usual RSA and Diffie-Hellman. I don't have answer. Why? You asked me why. I don't have an answer why. But I mean, it doesn't. It's not familiar. I mean, industry does not use it. Okay.
Usually people like solutions that are good and simple. This is not as simple as the other solution. You know?
I don't know. I really don't know. I don't know. I know that there are good people in Babylon, like Professor Lindell, that may have an answer. I tried to meet him several times, but he's a very busy man. Okay, I mean, I don't think about it too much because for me, the interest is mathematics. Okay, it's not really the industry. I mean, of course, it's very nice to have something in industry, but for me, the real interest, after all, is mathematics. So I don't care if it's being implemented or not. I mean, but I hope that if you a little play with this, maybe one day you can do something like this. I don't know. But anyway, this is going to be a little more or less the project. I mean, to create some software, I mean, some program that uses cryptography with using this such kind of extension of field. Okay. I will write it. I will write it very. I mean, I will write it explicitly. Sorry.
Yeah, I ask if there is something I don't know, like attack proved, like something that you can't break mathematically. You just like
no, you need the community. I mean, getting into it. I mean, there is no I mean, determined way to check. I mean, something is good if it was I mean, revealed and people try to attack it and didn't. This is the real test. Okay, this is the real test.
Yeah, because I'm getting a bit of the subject, but I know that like in quantum cryptography, you have things that are like physically cannot be decrypted. So maybe I don't know if in mathematics you have those kind of structure that.
I'm not a specialist in this. I don't know. Okay.
Okay.
Maybe it's worth to ask Professor Kuniavsky. Okay. Anyway, I think it's interesting. I mean, there are many things to talk about more, but we will end by now this lecture. I hope you find it interesting. I don't know. Anyway, you see how classical problems in number theory, you see that this was handled by ancient Greeks, okay, 2,500 years ago, using modern methods are being implemented, I mean, are being very useful in industry, or in modern industry. I mean, I think it's fascinating. I mean, this is my opinion.
In the next lecture, we will talk about how to the authenticity problem.
No. I'm not so special about these protocols. I'm only from the mathematics. Okay. So next lecture, we still have to see the elliptic curves. Elliptic curves today is the most popular protocol. I'm going to explain to you why. What is the advantage of the elliptic curves over the RSA, the Diffie-Hellman. Okay.
Okay.
So thank you very much.
Thank you.
And have a nice evening.
Thank you too.
Thanks.